Unit 7A, Probability, Definitions, and the Law of Large Numbers. A game or an experiment is an activity that has results. For example, a game might be roll a fair die once. The sample space is a set of all possible equally likely outcomes of that game. So the sample space, or the set of possible equally likely outcomes for that game, would be 1, 2, 3, 4, 5, or 6 when you roll a die once. Now, an event consists of one or more outcomes. So even is an event. What does even mean? Even means you get a 2, a 4, or a 6. 5. The event 5 means you get a 5. The probability of an event is a measure of the likelihood that that event will occur. And probability of an event is on a scale from 0 to 1. So here's our scale. If we have a probability of 0, that means the event is impossible, can't happen. If the probability is 1, the event is certain. So that's the scale. It goes from impossible to certain. In the middle would be like flipping a coin. You have an even chance of head. The probability of head when you flip a coin is 0.5, right in the middle. The probability of 0.25, that would be an unlikely event. And if an event has a probability of 0.75, that would be likely to occur. Now, these probabilities could be written in the form of decimals, in the form of fractions. This would be 1 out of 4 chance, 1 out of 2 chance, 3 out of 4 chance, or as percents. This would be 0% chance, 25% chance, 50% chance, 75% chance, and 100% chance. So you should be able to convert between decimals, fractions, and percents, because probabilities can be expressed in any one of those forms. Now, there are various ways to look at probability. One is intuitively, just using your intuition. So, for example, let's say here's the probability scale. It goes from 0 to 1. This is impossible. In the middle is an even chance, and 1 is certain. Now, if you say to yourself, there's a pretty good chance that I'm going to pass this class, I'm using my intuition to say the probability that I pass is pretty good. I feel very confident about that. Well, now you're talking about a number here. Maybe the probability is 80% or 90% if you're more certain, if you feel confident about the class. If, on the other hand, you say, well, look, he's asking that girl for a date. The probability she's going to date him is no chance. There's no chance that she's going to date him. So the probability that this person gets a date, if he's got no chance for this date, well, that probability is going to be something over here close to 0. Close to 0. That's using your intuition. Relative frequency is an empirical or statistical probability equal to the number of observations of an event in n trials. So, for example, you could flip a coin. You want to see if a coin is fair. So you flip a coin 100 times. That would be n. Then you take a particular event like tail, and you record the frequency of tail. How many times does tail come up? Well, maybe tail came out 52 times. Well, we would say the relative frequency of tails, or the probability of tails, is equal to the frequency over n. The frequency of tails was 52 out of n equals 100 trials, or 52%. And that might indicate to you, well, it's probably a fair coin because we came out to be close to 50%, which is what you would expect from a fair coin. Now, the most important definition of probability is the classical one. In this one, you take the number of possible outcomes for the game. That's the sample space, the number of possible equally likely outcomes, and you put that in the denominator, and on the numerator you put down the number of those outcomes which would be successful for that particular event. So, for example, the game could be flip a coin, the probability of tails. The probability you get a tail when you flip a coin. Well, when you flip a coin, there are how many different possible equally likely outcomes? There are just 2. That's the size of the sample space, so the number of possible equally likely outcomes. That goes on the bottom. And how many of those would be success in terms of tail? 1. So 1/2 is the probability of tail. Suppose we roll a die and we say, what's the probability you get more than 4 when you roll a die? Well, when you roll a die, what are the possible outcomes? 1, 2, 3, 4, 5, 6. There are 6 possible outcomes, so n is 6. How many of these would be successful in terms of being more than 4? How many of those 6 are more than 4? Well, here's 4, so more than 4 would be these 2. 2 out of 6. So 2 out of 6, or you could reduce that if you like to 1/3. There's a 1/3 chance, or a 2 out of 6 chance, that the probability when you roll a die, that the probability will be more than 4. Or I could say pick an object from a bag, blindfolded, and in this bag would be 3 red objects, 5 white ones, and 2 blue ones. And I could say, what is the probability that you get a red object? Well, how many equally likely outcomes are there to this game? Well, each of these balls is equally likely to be picked, so therefore there are 10 equally likely picks. How many of those 10 would be red? Well, 3. So there's a 3 out of 10 chance that you would pick a red one. Now, the law of large numbers says that when a game is repeated over and over again, the relative frequency, f over n, this gets closer and closer to the theoretical probability of that particular event. So, for example, if you flip a coin once, the probability of tails is equal to, well, there are 2 possible outcomes, as we said before, for flipping a coin. And of those 2, there's only 1 successful one. So the theoretical probability of getting a tail is 1/2 or 0.50 or 50%. Let's play this game over and over again of flipping a coin and see what happens. If you flip a coin many times, the relative frequency is going to come out to be a number very close to the theoretical value of 50%. You can do this at home by dropping 100 coins on the floor and counting the number of tails. Or you could flip a coin 100 times and record the number of tails, and then look at the relative frequency of tails compared to 100 flips. Or you can do a simulation, an artificial process that behaves mathematically like the actual process of flipping a coin. What we're going to do is have the calculator generate random integers between 0 and 1. In other words, it's going to generate a series of ones and zeros randomly. For us, a 1 is going to represent tail, and a 0 represents head. So every time a random number comes up, that's going to signify a head or a tail on a flip. Now, what we're going to do here is do a short run and a long run. First, we're going to, this should be a 10 here, we're going to flip a coin 10 times and see what the relative frequency is, f over n. Then we're going to flip a coin 300 times, and we expect f over n to be very close to the theoretical probability of heads, which is 0.50. So how would we do this using the TI calculator? Well, first you go to Stat Edit, and you bring the cursor not to the usual location, which is right below L1, but you navigate with the up arrow and put it right on top of L1, so that in the bottom area down here, you'll see L1 equals. And the machine is asking you, what do you want L1 to be? Now you do math probability, go to number 5, random integer. And what we're going to do is type in, the way random integer works is you type in the low end, the high end, and the number of times you want to do this. So the low end would be 0, the high end is 1, and let's say we want 10 flips. So you would enter that 0, 1, 10 with commas in between. It'll look like this. Hit enter, and you will see the machine will have put in 10 randomly selected zeros and ones. And don't forget, the 1 means tail, 0 means head, 0 is head, this is tail, and so on. Now we want to calculate how many tails we got. So we do stat, calculate one variable, as usual, and then we tell the machine that we want the machine to look at L1, that's the list, frequency list you leave blank, and calculate, and you get X bar is 0.6. Now what is X bar? That would be the sum of the scores divided by the number of scores, which in this case was 10. So the sum of the scores, wouldn't that just represent how many tails you got? Because every time you got a tail, you got a 1 and zeros for heads. So this would be the number of tails over n. So that's f over n. That's the relative frequency. And that came out to be 60% in the short run. Now 60% is not 50%, but it's pretty close. You can go home and do this yourself. You'll get a different value for f over n. But it's hard to tell what's going to happen in the short run. What the law of large numbers says is, in the long run, the relative frequency is going to come out to be very close to the theoretical probability. So let's try this again, but this time we're going to substitute 300 for 6. Well, you can do the same steps over again, and when I did it, I got 0.48. Now you're not going to get 0.48, but you'll get something close to that. Now 0.48 is very close to 50%. And this verifies the law of large numbers. You try it yourself and see what happens. That's the end of Unit 7A. See 7B for the not and rules for probability.